Hello everyone, and welcome to Topic 9, the second to last topic of Competitive Programming 1. Today we're going to be talking about breadth first search, or BFS for short. And it could be seen as a problem-solving technique that is the complement to depth first search, or DFS, which we talked about last time. And if you remember, DFS had us explore as far as possible down a single path before backtracking to find other paths. BFS sort of works the opposite way. Instead of going as far down as possible, it explores every single path at the same time, at the same rate. And just like a DFS uses a stack or recursion, which uses a call stack, we use a queue, the opposite data structure, to implement a breadth first search. And to show you what we mean, let's just jump straight into our first example, which is just going to be a simple BFS. You are on a 5x5 grid, and if you can only move directly up or down or left or right, what is the least amount of steps it will take you to get to each cell of the grid? So we might start here. We have a grid that's all negative ones, just for unexplored, and we might start at this square right here, 0, because we are already on the square, won't take any steps to get here. And our completed grid might look like this, right? So we have our 0 again in the same location. Then there are cells, these cells, the exact neighbor cells, will take exactly one step to get to. And then these cells, these 2s, well, they will take exactly one step from the 1s to get to, so they have 2 steps to get there, and so on and so on. So how might we accomplish this using a breadth first search? Well, first, we're going to create a queue and then add the first cell to it. Then, while there are still cells to be explored, or the queue is not empty, the queue still has some cells left in it, we just remove the top of the queue and check for in each of the 4 directions that we can move, right? If any of them had not been visited, then set its distance just 1 plus the previous cell's distance and add it to the queue, add it back to the queue. So essentially what this does is explores all cells with distance 0, then explores all cells with distance 1, then all cells with distance 2, and it's sort of like expanding out from the original cell here, right? So we might add this original cell to the queue first. Then after we process this one, these 1s would be added to the queue. After we process each one of these 1s, you can see that each one of them, all its neighboring 2s, would be added to the queue, and so on and so on. Now, let's just write this down in code to see how it might work. Okay, so as before, I've just written some starter code, mostly just the print array function or method that will print a 2D array for us, and a main method that will print the result of our breadth first search on when we start at row 1 and column 2. So first things first is to create the grid of negative 1s. I've already copy pasted it so that I don't have to do as much typing. Then we would set the original cell to equal 0. Right, because that's the original cell, and then create a queue for the breadth first search. New linked list. And finally, add the next, the first cell to our breadth first search queue. Then let's also create our DRDC array so that we can traverse in the 4 directions efficiently. -1. Okay, cool. And then we will just run our breadth first search while our search is not empty. Right? And so first things first, VS Code is going to be dumb and tell us that method is empty is undefined, but really it's a queue, of course it's defined. We remove the first element off the queue, the breadth first search queue. And I'm just going to assign each of these variables so that's easier to think about. So the row is going to be the first one, the column is going to be the second one. Yeah. And then for int I equals 0, again using our DC arrays to explore in all 4 directions. Let's just have new row is equal to r plus dri, new column is equal to c plus dci, and if it's inside the bounds, right? So inside the bounds means it's new row is less than or equal to 0, or sorry, greater than or equal to 0, and new row is less than 5, and 0 is less than or equal to new column, and new column is less than 5, and one actual final one that we need is that our final cell, or this new cell, the new cell and C is unexplored. So this means that it has to equal -1. So if all of these conditions are true, then we just set this distance equal to the original, the previous point plus 1, right? So we're advancing it by 1 step, and then we add this new cell back into our grid. Yep. And that is it. That's it. It will do everything for us. While there are still cells left to be explored, it's going to explore all of the cells possible. And at the end, all we have to do is to return our grid and see what we get. And finally, let's run our main method to make sure it really works. And there we go. We have our 0 here, and 1's on the outside, 2's in the next ring, 3's in the next ring, and so on and so on. Our second example is going to be another typical application of a BFS, just to get you familiar with the concept. So here, it's rings. You are given a cross-section of a tree trunk. Tree trunks can be divided into rings going from out to in, and label the trunk with its respective rings. And initially the tree trunk area is labeled -1 and the outside area is labeled 0. So you might get a 2D array that looks something like this, right? So we have a tree trunk in this area right here, the gray spots, and then outside the tree trunk are the white cells. And again, we could just breadth first search, except this time we just initialize the queue with all of the 0 cells on the outside, right? Because essentially all we have to do is to explore from outside to in. Now, we also need to take care because there are also cells on the outside that should have a distance, or sorry, a ring of 1, but they're not touching any 0 cells. So we can just also, after initializing all of the 0 cells, initialize the 1 cells that are on the outside border, right? Like these 2, these 4, this one, and this one. So, like, for example, these 2, these are 1s, even though they're not bordering any 0 cell, we just need to make sure that they stay 1s and aren't forgotten about. So here we have our starter code again. It's pretty much the same, except here we just have our grid. If you look carefully, it's actually going to be the same as as the example that we saw on our slides. So first thing I'm going to do actually is going to pull out the number of rows and the number of columns, just so that it's easier, more easily accessed, right? And then add our make our BFS queue again. Right? And then add all of our 0s to our BFS search. So iterate through the entire thing for int I equals 0, I is less than r, I plus plus, for int j equals 0, j is less than r, or j is less than c, the number of columns, j plus plus. And if we have this specific cell, oh, not trees, it's grid. if this specific cell is 0, then we just have to add it to our BFS. New int ij. Cool. Now we also need to add the outside ones, right? If you remember here, these cells on the outside aren't bordered by any 0, but they should still be labeled as ring 1. And we need to make sure of that. So let's just add all of those on the outside as 1. So we're going to iterate through all rows first. And if the one on the left is a -1, very left is a -1, we're going to set it to 1. I keep forgetting that's not the right variable. We should set this equal to ring 1, and then add it to the BFS search. And we continue to do this on all sides, right? So this side is actually going to be, this side is actually going to be, we're iterating through all of these, then we should just iterate through all of those, and those, just to make sure. And I'm not going to type it out here, I'm just going to skip forward because it's very boring. Now that that's done, I want to emphasize that this actually only works because we are processing the grid cells with that are 0 first, and then the grid cells that are the 1s. This is because we want to make sure that we explore all the 0 cells before we exploring all the 1 cells, and if we do it all the other way around, then we might eventually end up exploring to a 2 cell, a quote-unquote 2 cell, from these 1 cells that are actually neighboring a 0 cell. So this means that they should have been labeled 1 cells, but instead are labeled 2 cells because we explored the 1 cells first. So again, this only works because we are doing 0s and then processing all the 0s and then processing the 1s. Now, the BFS is actually very similar, so similar actually that I am actually just going to go and copy the code from the previous example, because the BFS is going to be the exact same. So when we run this, we'll see that even though we didn't modify the breadth first search at all, it still does it does what we want it to do, because breadth first search is, as a strategy, is actually pretty simple and can be extended without changing that much. So you see here, we would have our tree trunk, and again, the outside is ring 1, next one is ring 2, and on the very inside is ring 3. So let's do a few comparisons of depth first search to breadth first search. As mentioned before, DFS explores as far as possible down a single path and only backtracks if you find a dead end. And because of this, DFS is not guaranteed to find the best solution. You might end up taking a huge detour moving from point A to point B and ignore a shorter path just because you didn't explore that path first. For example, if you're in a maze and you just go down every single path, well, sometimes you're going to find the exit really quickly, but sometimes you're going to like loop around for a long time instead of taking a shortcut that's right there that you just for some reason didn't explore. However, BFS is always guaranteed to find the shortest solution because it explores all the cells at the same rate. And so if you want to find the shortest path, you want to use BFS, but if you're only looking for a single solution, like if a solution is possible or not, then DFS is going to be fine because it's going to be faster than just, exploring in so many directions. And this brings us to example 3, shortest bridge. In a given 2D array, there are 2 islands formed by 1s. We can change 0s to 1s to connect the 2 islands together to form a single island. Return the smallest number of 0s that must be flipped. So in this example, we have 1 island here, another island here, and well, what's the shortest path, right, from one island to another? We can think about this way. Well, we just need to this would be the shortest path right here, these two zeros. So we would return 2 because we would only need to flip these two zeros to 1s in order to connect the two islands. Anywhere else, you would need to connect 3. Like here, you need to connect 3, 3, 3, but here you only need to connect 2 to connect the shortest islands. And so how might we solve this problem? Again, you might think using using breadth first search, right? So we first just iterate through the array, go through every single cell checking for a 1, and we flood fill it to a different number to distinguish the two islands, and just to make sure that we can tell the two apart. And then we also add all of the cells that we find to the BFS queue, and then we just BFS before, and we terminate when we find a cell belonging to the other island. And this is going to be guaranteed to be, again, the shortest distance between the two islands, because you are going to find this first. And for this question, I'm just going to eventually end up setting the first island to -1 instead of 1, and then BFS by subtracting 1 every single iteration instead of adding 1. So again, this is basically the same thing as before, but this essentially allows me to distinguish the two islands and make sure that any of the values don't overlap, right? You might be able to accomplish the same thing by setting the first island that you find to 2 and then go to 2, 3, 4 and add 1 like that. But I'm just going to use negative values because it makes the most sense to me. And in general, whenever you see like least amount or shortest path or fastest solution, well, you're going to be using BFS to find it. Okay, so step 1 of this process is going to be finding the first island and then flood filling it to all be some other number, aka -1s. So what we're going to do is just, first off, I'm going to write a flood fill function because using a recursion to flood fill is actually much easier than doing it the other way. So public static void fill, and we're going to have the map, the row that we are on, the column, and a queue to add it to the BFS queue. Cool. And I'm also going to be putting the dr/dc arrays outside just because I'm going to need to access them in both fill and bridge. -1, 0, 1, 0, and dc is equal to 0, 1, 0, -1. All right, cool. So let's just start off here. So we need to first set our map.length. C is equal to so like before, setting the rows and columns for easier access. And then we're going to iterate through and find the first one. So find the first island. So for int I equals 0, I is less than r, and I++. For int j is equal to 0, j is less than c, j++. And if we found an island, so if map ij is equal to 1, then we're going to flood fill it. So flood fill it, fill map. Oh, we didn't make our BFS array. So let's BFS queue. Let's just do that first. BFS equal to new linked list. Yes. Okay, so we're going to fill the map at the current location ij, and also be using this BFS queue. And we're going to break after this because we have found a first island. And to break out of the second for loop, I'm just going to create a boolean to see if it's found or not. And we're just going to set found is equal to true here. And outside of this for loop, we're going to check if found, then break as well. So we break out of both. Now let's write our flood fill. This needs to be capital. Let's write our flood fill. So flood fill, we learned about this in last lesson. It should be pretty easy, but I'm just going to write it down here just to review. So we set the current cell to our value. Remember, I'm just choosing to pick -1 and then BFSing eventually into negative numbers. Then we add this to the BFS queue, RC, and then we check in all 4 directions as before. For int I equals 0, I is less than 4, I plus plus. We have int new row is equal to r plus dri. New column is equal to c plus dci. And finally, if we are in bounds, oh, we should probably also copy this in here so that we can access it to check the inbounds better. 0 is less than or equal to nr, and nr is less than rows, and 0 is less than or equal to nc, and nc is less than the number of columns, and we are still on the island, right? So map nr nc is equal to 1. So if all of these conditions are true, then we're going to flood fill into the next area. BFS. Cool. So again, this is just a simple flood fill. You should remember this from our previous topic 8 lesson. Now, our breadth first search, again, is going to be pretty much the same. However, there's going to be some slight differences from before, so I can't just copy it in. So, but the overall structure is the same. Breadth first, while the BFS is not empty, we remove the first one, and let's just set some variables again. Now, we just try to visit through every single one of the squares, right? For int I equals 0, I is less than 4, I plus plus, and we have our int nr is equal to r plus dri, int nc equals c plus dci, right? New row, new column. If it's all in bounds, 0 is less equal to nr, and nr is less than r, and 0 is less than or equal to nc, and nc is less than c, right? And we are on a unexplored space this time, right? Because we are BFSing from the first island to the second island, so we only want to traverse over zeros to find the shortest bridge. So map nr nc is equal to 0. So if all these conditions are true, then we just set nr nc this equal to the distance. And remember, we're using negative numbers here, right? We're using negative numbers, so we want a -1 instead of +1. But we still add it to the BFS queue to be explored later. nr nc. Beautiful, beautiful. And if we actually find the other island, so actually let's take this out. So if it's in bounds, we should check if it's in bounds here, right, first. So if we don't find the other island, if we're still exploring here, then let's add it to the queue. However, if we do find the other island, nr nc is equal to 1. Remember, the other island will be still 1s. We flood filled the first island with -1, but the second island should still have just 1. Then we return the negative, right, because we're using negatives, map nr nc. Actually, sorry, not return nr nc, return rc. And of course, we want to subtract 1 at the end, because if you think about it, when we started the BFS, our first island was all flood filled with -1s, right? So we're including an extra -1 in there that we shouldn't be. So after we invert it, we have to subtract away the extra 1. And at the end here, let's just return a -1 if we can't find the other island. And let's run this code and see what output we get. This grid is going to be the same as the example that we've seen, and it of course should return 2 like we had seen in the slides. Now, breadth first search isn't just limited to finding the shortest path on a grid. It can actually be thought of as a general problem-solving technique that can be used whenever you're transitioning from state to state in a problem, and you need to find the shortest number of moves or the least number of steps to get from state A to state B. And while the general breadth first search structure is going to be staying the same, what will change is the way that you store the data and then the way you move from one cell to all its neighboring cells. And I'll be going over 2 examples to show you what this concept is all about. So our first of the 2 examples is going to be perfect squares. Given a positive integer n, find the least amount of square numbers needed to sum to n. So essentially this means that, let's just say we were given the number 13. Well, 13 can be written as 4 plus 9, so that's only 2 square numbers needed to sum to n, and you can show that it's impossible to find 1. 12, would give an answer of 3 because 12 can be written as 4 plus 4 plus 4, 3 square numbers, and 11 can be written as 1 plus 1 plus 9, so again, 3 square numbers. And again, the least amount of square numbers. You hear least amount, you should be thinking breadth first search. So we can imagine we start at a number, and every single neighbor that we traverse to is going to be the addition of another square number. So if we're at some number x, then we just check x plus 1, x plus 4, x plus 9, and so on until x plus I squared is greater than the target number n. And eventually, when we reach the number n, we just return the number of steps it took to get there. Okay, so for this first example, remember we're not actually going to be using a grid, we're BFSing over the integers. And, well, what better way to BFS than just to use a regular array? So we're going to create a nums array, int n plus 1. We're using n plus 1 because we actually want to find if there's n. So basically we want to have this array represent numbers from 0 all the way to n, and the way to do that would just be to have n plus 1 entries. Then we set num0 is equal to 1. Obviously it will take 0 numbers to reach 0. It should be nums. However, we need to use 1 to differentiate it from the zeros, and we'll just subtract 1 when we return it later. Then we're going to make our BFS queue. New linked list. And add 0, the starting number, to the queue. And BFS, again, is going to be quite similar. While the BFS is not empty, int cur is equal to, so we remove the first number off the queue, and then we iterate from I equals 1 to, and while cur plus I times I is less than or equal to n, right? So this will make sure that this number doesn't actually go over, so the new number doesn't actually go over our target number, so we don't explore farther than we have to. And then I++. So this eventually will explore, cur plus 1, cur plus 4, cur plus 9, etc., etc. Then we just say, like, int new cur is equal to cur plus I times I. Yeah. Okay. Then if this new number has been unexplored, nums cur plus I times I is equal to 0, right? We've never seen this yet. Then we let nums cur, or I should be using new cur, is equal to nums. So we find so this is the number of numbers that the previous number had added up to, plus this new one. That's a tongue twister. and then bfs.add cur new cur. So like before, this BFS is going to be actually pretty similar to what we had before. And finally, if after that we saw that the target number, it was no longer 0, so this means that the BFS had reached it sometime, then we just return nums, so the number at 0, and finally -1. Remember, we started off with 1, so we have to subtract that 1 later on. And if somehow we can't find however many squares, we just return -1. But that's impossible, but you know, who knows. So let's run. What do we get? And as expected, we get 3, 3, 2. 11, 12, 13. And for our second example, I'm actually going to be going over another breadth first search technique known as layered BFS, or also known as 0-1 BFS. This is because we're not actually going to be storing the distance from the start inside the array. Rather, we're only going to be storing 2 values, 0 for not visited and 1 for visited. And to keep track of how far we've moved from the start, we're going to keep some layer variable and process the BFS queue 1 layer at a time. So we have all zeros processed first, then we advance it to layer 1, we process everything in the array, do it again, and so on and so on. So this way we can still keep track of which layer we are on, even though we're only using 1 variable to store it. And for our example, it's going to be open the lock. You have a lock with 4 circular wheels with digits from 0 to 9 each. The wheels can rotate freely and wrap around, so this means that we can turn 9 to 0 or 0 to 9, and each move consists of turning 1 wheel, 1 slot. The lock initially starts at 0, 0, 0, 0. You are given a list of dead ends, meaning if the lock displays any of these codes, the wheels of the lock will stop turning and you will be unable to open it. And finally, given a target, return the minimum total number of turns required to open the lock, or -1 if it is impossible. And BFS, it should be pretty simple to figure out, right? Every 1 turn of a lock wheel should be an advancement to the next state, an advancement to the next layer. And of course, we shouldn't advance it to a deadlock if possible, because then we can't turn it, that would be a fail. So an example here might be, here's a list of dead ends. We want to move from 0, 0, 0, 0 to 0, 2, 0, 2, and it would actually take 6 turns. Because if we were just to do it directly, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, 0, 1, 0, 2, and 0, 2, 0, 2, well actually this is a dead end, so we can't actually turn the wheel, or turn any of the wheels after we reach this state. So what we have to do is actually turn the first wheel once to avoid all of these dead ends, and then turn it back at the end. So that would take actually 6 moves instead of 4 if we had just turned it directly. And we're going to be using layered BFS as will be shown. As usual, I've written up some starter code with the example that we had on the slides. So, open lock. Let's start off by creating our states, our lock states. We can have from 0, 0, 0, 0 to 9, 9, 9, 9, so we're just going to initialize an int array of 10,000 because that's how many we have. Then we're going to add all of our dead ends in. So for each dead end in dead ends, we're going to set the state and we're going to change it from a string to an integer so we can use it as an index, set it to -1. We're actually going to have 3 values here. 0 for not visited, 1 for visited, and -1 for a dead end or can't explore past. Then we're going to turn our target into a goal because we're given all strings here. Okay, cool. Then we also need to check some edge cases, right? So if if the goal is actually a dead end, or the start is a dead end, well, let's just immediately return -1 because it's impossible. Then let's just create our BFS queue. And start at 0, 0, 0, 0, 0. Because that's our starting location, so 1 for visited, add it to the BFS. And of course, we need our layer variable. Int layer is equal to 0, because currently we are at layer 0. So, while the BFS is not empty, as usual, we're going to increase the layer count because we're going to start exploring on a new layer, right? And then we're going to actually pull out the size, bfs.size, and iterate through the entire thing. So for int I equals 0, I is less than size, I plus plus, we're going to do our BFS. Now, notice how I pull out the size beforehand. This is because during our BFS, we're actually going to be adding items back into the queue. So if we put this BFS.size in here, well, we're going to be actually iterating through an incorrect amount of elements because this will end up changing as we go on through the BFS. Okay, so we remove the current one, right? So how are we actually going to iterate through each of the different combinations that a single turn can bring this to? Well, we're going to just write a helper function. So public static int turn wheel, and our initial state, maybe the wheel that we are going to turn. So 0, 1, 2, 3, the first one, the second one, the third one, the fourth one. And then in the direction, so direction maybe -1 or +1, depending on whether you're turning it up or down. Now we're also going to make a wheels array, static, a wheels array, indicating which wheel we're turning, right? So 1000, 100, 10, 1, and because if you think about it, if we have like these numbers, like this is a state, then this wheel, this would be the first wheel, but it would be the thousands place. This 9 would be the second wheel, but it would be the hundreds place. So we're essentially assigning each wheel number to a actual value that we can deal with. So we can actually, I'm going to just set, so the current wheel that we're dealing with, what is the wheel that we're dealing with? Well, it's going to be state divided by wheels. And so basically this is going to take the wheel number, pull the correct wheel from it, and divide it by this. So this gets so again, if we had like a random number and we were trying to look at the second wheel right here, well, if we divide this by 100, we would get 32, right? And we only want the last digit now. We only want this digit. So we just mod it by 10. So eventually, if we mod this by 10, what do we get? We get 2. We get the wheel that we want here. Cool. Then we want to turn the wheel. We just turn the wheel in the direction, right? So if we're turning it up, it's +1. If we're turning it down, we -1. So that should just be cur plus direction. And we will actually want to mod it by 10 because if it turns from 0 to -1, we want to return 9. If it turns from 9 to 0, well, 9 to 10, we actually want to return 0. And we're going to add a 10 in here just in case for the modding protection. And finally, we just return our original state minus the previous wheel, right? So cur times wheel, and then add on the new position of the wheel. like so. So essentially this resets the wheel back to 0, and this changes it to the new position. And so this turn wheel method right here is going to return the wheel's state after we turn a specific wheel in some direction. Okay, so now let's iterate through all possible values. Or all possible, state movements or wheel turns or whatever. So first, we can iterate through, we can turn each wheel, right? So this is wheel 0, wheel 1, wheel 2, wheel 3. And we can also turn it in a direction of -1 to 1, or -1 or 1. So I'm actually going to do for int j is equal to -1, j is less than or equal to 1, and then j plus equals 2. Actually, I don't want to be using I and j here because, I mean, it might mess with some previous variables. Let's change this to W for wheel and D for direction. Right, so this is a funky for loop, but all this does is we have -1, then after the next loop we add 2, so then we get 1, and then it will terminate. So this will just make sure the direction is -1 or 1. And we have the next state is going to be the turn wheel, right? So our function we wrote, our original state, and then the wheel that we have, and then the direction that we have. Now, if next is goal, right? So if we've reached the goal right now, then we just return this layer that we're on, right? Because we've already reached it. We know that it takes exactly that many steps to get to it. However, if not, else if it's not, if it's not the goal and it's not visited, so this next turn is not visited, then we just add it and do the same thing, add it to the queue, mark it as visited. So mark it as visited, states next is equal to 1, and bfs.add next. And that should be our breadth first search. Oh, one more thing actually. At the end right here, if this loop exits before we find a solution, which means that our BFS queue is empty before we find the goal here, then that means it's going to be impossible. That means the dead ends are blocking all possible paths, and we're going to return -1. Oh wait, cool. So that should be it. And let's run this code now then to see if we get 6 like we have seen on our slides, and we do. So we know that this is going to be correct. And that is going to be the end of the lesson today. Remember, the homework set on HackerRank is due July 29th, so remember to log on and solve those problems. And well, even though there's one more class, this is actually going to be the last one that's going to be taught by me. So thank you all for taking this class over the summer, and I hope you guys learned a lot. Bye-bye.